Also, in the context talking about lighter elements, in the case of heavier elements, you cannot ignore the interaction between the electrons. With heavier elements, the electrons move faster, so you get relativistic effects, and the strength of the interaction between the electrons, they're electrons, right? Same charge, so they repel each other, and so it works out with a full relativistic treatment of quantum mechanics that you can't ignore the strength of the interaction between the electrons for heavier elements. Okay, so with the relativistic treatment, the high energy, high speed electrons in heavy elements, the inter-electron interactions need to be considered. But for the lighter elements, that's not the case. Now, again, this is just giving you a taste of what's coming with graduate level spin-orbit interaction. You can draw diagrams that help your thinking somewhat. Now, remember J, the total angular momentum is the sum of, let's say, keeping it simple, just two components, J1 plus J2. In this case, we're talking spin-orbit interaction, so we have a spin angular momentum and an orbital angular momentum, so an S and an L, and so you can look on J here as the total angular momentum, which is L plus S. Think of them as vectors. Now the eigenvalue for L hat, or L squared, L hat squared, is L into L plus 1, probably remember. So think of this length, if you think of it as a vector, as square root of L plus 1, and you probably remember the eigenvalue for S hat squared is 3 over 4, or 3H bar squared over 4. Okay, so think of the length as then just the square root of S squared, so just root 3 over 2 square root of 4, right? So this is J, thought of as a vector. Now you may wonder where this size comes from. Well, you've got to go back to the theory of previous. Now I'm not expecting you to understand. Well, you could try it if you like. Go back to the theory of a couple of sessions back, which got pretty heavy. But this is just giving you a taste. Now this sort of thing, full or more complete treatment of spin-orbit interaction at graduate level, you would be able to calculate this, the length of this, given your L has size little l, its eigenvalue, and S of root 3 over 2. Then, so if your orientation of your spin is up, so in a sense parallel in inverted commas, it's not strictly parallel with L, it's not like that. You can't have S being in the same orientation of L for, discussed that earlier, but it's orientated up in a sense rather than down. Okay, so then your J, this length, so to speak, would be this, and you calculate these numbers here from the earlier theory once you've got full knowledge of how to do that, but you don't have that at undergrad level. Anyway, just to give you an impression of what's coming. You can use diagrams like this that help you with talking about spin-orbit interaction. Now, if your spin is sort of anti-parallel, again parallel in inverted commas, like spin down, then your J will be less. And you can see that qualitative. Well, here you got plus 3 over 2. Here you got minus a half. So this term L plus a half is the same. So you expect it to be smaller because your vector addition, in a sense, this plus this gives you this. This will be shorter, obviously, than this one. Okay. Now these two diagrams for the case when your little j, is little l plus a half. Similarly here, but here your spin is, inverted commas, parallel to L, and here it's anti-parallel, so you'll get different J's. Right? You're probably not too clear on what this is about, and that's fine. It's just to give you a taste of what's coming at graduate level. Right? Well, now for the next couple of sessions, we're going to talk more in detail about the spin-orbit coupling. So there's an interaction between the two magnetic moments. So, saying a bit earlier, say for the electron spin, imagine charge inside the electron. Now, that's a crude classical analogy, but trying to imagine where the magnetic moment of the electron comes from, due to its spin. So imagine this charge whizzing around, so that's swirling, looping current, and that acts like a little magnet. So you imagine, so the spin of the electron generates sort of magnetic phenomenon, a magnetic moment, right? And similarly to its orbital angular momentum, because it's whizzing around the nucleus. Okay? So you have two magnetic moments. There's a magnetic moment due to the whizzing around of the electron around the nucleus, and so you could call that the magnetic moment mu L, right? And due to the magnetic due to the spin, call that mu S. So you have these two magnetic moments. Think of them as vectors, and to get the potential energy, the interaction energy of these little magnets, if you like, in a magnetic field, they'll feel a force on them due to the magnetic field. Then you just take the dot product, scalar product, of either of these magnetic moments, dot the magnetic field strength, B, as a vector. So it'd be mu dot B, or mu L dot B, or mu S dot B. So now these get rewritten in the following way. Well, the magnetic moment comes from the angular momentum. So in terms of the electron whizzing around the nucleus, let's say, these are effectively constants. In fact, this GL is put in there. In fact, it's only 1. Yeah, it's just equal to 1. So effectively, the physics is the magnetic moment. The magnetic moment comes from the angular momentum, and this mu B here is a symbol. We've done that before. It's the Bohr. The little b here is for not magnetic field, but Bohr, Niels Bohr. It's the Bohr magneton, which is defined. So 3 bars. And we've done this before. It's just the charge of the electron times h bar, Planck's constant, divided by twice the mass of the electron. Okay, so that's just the definition of the Bohr magneton. So it's that times the angular momentum of the electron about the nucleus, right? Now we have a similar expression for the, I'll turn around. Have a similar expression for the magnetic moment due to the spin. So here's your spin, and again the Bohr magneton here, and this GS here, which is in the case of spin, it's 2. Why is that? High stuff. Don't worry about it. Okay. So for the orbital angular momentum, this G factor is 1, and for quantum field theory, Dirac equation type relativistic reasons, GS is 2 in the case of spin. Don't worry about it, it's high level stuff. Okay. Now the interesting thing is these two magnetic, well, mu-L and mu-S, they interact like in a manner of speaking. The one generates a kind of force on the other, right, or potential on the other. So you get a kind of interaction between the two. Now the potential energy, the potential of this interaction is fairly small, especially compared with, say, the differences in energy levels, say, in the hydrogen atom. So corresponding to your little n, which your quantum number labeling the energy levels, the quantized energy levels in the hydrogen atom, for example. So compared to compared to the difference in those energy levels, n1, n equals 1, n equals 2, n equals 3, in that sense, the energy correction, the perturbation, if you like, a small change, delta E, is pretty small compared to the energy differences due to in the energy levels of the hydrogen atom. The difference between E1 and E2, E3, and so on.